So in first year we talked about polar and nonpolar bonds, and nonpolar and polar had to do with the shared electrons between the two atoms and whether they're shared equally or not. So when you have a nonpolar bond, if you have two hydrogens pulling on those shared electrons, they end up right between the two atoms, and there's no charges at all in the molecule. All the electrons are equally shared, and that's a nonpolar covalent bond. A polar covalent bond is when one atom or the other is pulling more on that pair of shared electrons in the bond than the other. Chlorine is closer to an octet, so the electrons in this bond actually get pulled a bit closer to chlorine, and that creates a little bit of a negative charge for chlorine and a slightly positive charge for hydrogen. These charges are nowhere near a +1 -1 ion, but they're small charges because the electron is pulled closer to the atom that's closer to an octet, has a stronger pull on those shared electrons. So in a larger molecule like this, we can look at the bonds polarity, and we can also look at the whole molecule polarity. So carbon and hydrogen, carbon has 4 outer electrons, hydrogen has 1, and so carbon is actually closer to a full octet, and so the electrons in these bonds are all going to pull in toward the carbon a bit. And so it creates this pull. So there are definitely polar bonds in this molecule, but the entire molecule overall is nonpolar. If you think about this pull of negative electrons going this way and then going back out this way, it sort of cancels out. And this entire molecule would be nonpolar. The bonds are polar, but because of the symmetry of the molecule and the direction of those pulls of the electrons, the entire molecule is actually nonpolar. Now in this molecule, you have one of the things that can make an entire molecule polar. Between nitrogen and hydrogen, nitrogen has 5 electrons, hydrogen 1. And so because nitrogen has more valence electrons, the electrons are pulled more in the bond toward nitrogen on all 3 sides. That leaves the hydrogens a little bit positive, and that nitrogen would be a little bit negative, but there's also this unshared pair. This unshared pair is a huge area of negative charge. And so this molecule, even though it's not symmetrical, if it had a hydrogen, a 4th hydrogen, it would maybe be symmetrical. So it's unsymmetrical, and it also has this unshared pair. The unshared pair is a very negative area to this molecule. So we have a negative area at the top by the nitrogen, and then the slightly positive areas near the hydrogens. So that's what polarity means. A polar molecule has a plus and a minus end to it. It has plus and minus poles. So if you draw a Lewis structure and you see an unshared pair on the central atom, then you'll have a polar molecule overall. Nothing can cancel that unshared pair, not even another unshared pair on the center atom. That would just make it more polar. So this molecule, the entire molecule, is polar. So now in this molecule, again, electrons in the bonds are pulled more toward the chlorine, so we kind of drew these little arrows to show that. So we have a little bit of a positive charge on all these hydrogens. But now if we had another hydrogen at the top, if we had CH4 like we did before, we would have a symmetrical molecule, and it could maybe be nonpolar overall. But because this 4th bond is a carbon-chlorine, we're going to have a little bit of a polarity going on. The carbon and chlorine has 7 electrons, so the pull on the shared electrons is definitely out toward the chlorine, which means that chlorine is a little bit slightly negative. And so you can see we have a plus and a minus end to these molecules. The chlorine end is negative, the hydrogen ends are slightly positive, and so this entire molecule is polar. So there are 2 things you look for in a molecule to tell whether the entire molecule is polar overall. Even though it has polar bonds, a compound can be polar or nonpolar, but it's polar if you have different elements around the outside of the center atom, like we have in this case, or if you have an unshared pair in the center atom, like the NH3 that we did before. So in the worksheet, you'll draw several compounds and tell me whether the bonds are polar and whether the entire molecule is polar or nonpolar. In this case, the first one, Cl2, you have the same atom on each side of the bond, and so there's going to be an equal pull on the electrons. So the bond is nonpolar, and since all you have is that nonpolar bond, the entire molecule must be nonpolar also. So both are nonpolar in that case. In the molecule PCl5, the chlorine is closer to an octet than the phosphorus, and so the pull of the electrons would be more toward chlorine, but that's going to happen in all of these cases. This is a symmetrical molecule because every bond has a chlorine at the end of it, and so the bonds are polar because they're bonds between different elements, but the entire molecule, because it's symmetrical, and remember there has to be an unshared pair on the phosphorus to be to have it be polar, or it has to have different elements around the outside, and we don't have any of those cases here. So this entire molecule that's symmetrical is really appears to be nonpolar if viewed from the outside. So it doesn't really have a positive negative end to it at all. When you have big carbon compounds like this, you're just going to have three central atoms rather than just having one like we do in the smaller molecules. When you look at the three carbons, they join to each other. What they're trying to say here is when it reads as CH3, is that there's a carbon with 3 hydrogens around it. The next carbon is CH2, so this carbon has 2 hydrogens attached to it. And the third carbon is also a CH2, but then it has this chlorine on the outside. So you have to look at each of the carbons as if there are central atoms. Between the carbon-carbon bond, that's nonpolar because it's just carbon pulling on carbon. That's a nonpolar bond. But the others are going to be polar. Carbon is closer to an octet, and so there's a pull of these bonded electrons in toward the carbon. And then it's not a symmetrical molecule, though, because instead of having another hydrogen here on the end, you have a chlorine. And chlorine is closer to an octet, so there's a pull here. So all of these hydrogens are slightly positive, but the chlorine is slightly negative. So you have 3 different bonds going on. The carbon-carbon is nonpolar, the carbon-hydrogen is polar, and so is the carbon-chlorine. But the entire molecule, it will be polar because it's not symmetrical. You have that different end with the chlorine. So again, even though there's 3 different central atoms, if there's anything different on the outside, like this chlorine, it will make the entire molecule polar. This is an example of a carbon-hydrogen compound that would be nonpolar. The carbon-carbon bonds, again, are nonpolar. All of the carbon hydrogens would have this pull in, and you have the same elements all on the outside. So the 2 times we have molecules that are polar is if you have unshared pairs, like these 3 carbons. If there's any unshared pairs on the central atom, then you would have a polar molecule. Or if you have different elements around the outside. All the outer elements in this case are the hydrogens, and so the entire molecule will be nonpolar, even though there are polar bonds contained in the molecule.